Evening, everyone. Let's see. I don't know if let me know if the stream is good, Jerry. But yeah. So here we have the today we are going to go over reverse engineering. As I mentioned earlier, wow, that is very yellow. Let me there you go. So I have the questions here, or I have a link up here that you can visit, and that's for if you have any questions throughout the presentation. I won't be using this the entire time, so wow, when I move to the just get off the slides, this should still be up. You just won't be able to access the link. So just save this one right now. If you think you might want to ask questions. I have the questions and I'll try to here, keep that. I have a link up here that you can visit. And that's for if you have any questions throughout the presentation. So here, this is reverse I won't be using this first of all, the entire time. So again, ask to sign up to the QR code or the link. Get off the slides, and this should still be up. You just won't be able to access the link. So just save this one right now. If you think you might want to ask questions. I have the questions and I'll try to here, keep that. I have a link up here that you can visit. And also, and that's for if you have any questions throughout the presentation. This is reverse I won't be using online. You can also entire time. So ask questions. Ask to sign up to the QR code or the link. Get off the slides, and this should still be up. You just won't be able to access the link. So just save this one right now. If you think you might want to ask questions. I have the questions and I'll try to here, keep that. I have a link up here that you can visit. And also, and that's for if you have any questions throughout the presentation. This is reverse I won't be using online. You can also entire time. So ask questions. Ask to sign up to the QR code or the link. Get off the slides, and this should still be up. You just won't be able to access the link. So just again, this is just copied right now. But in more detail, if you think for resources, I have the so first of all, I have a link up here that you can visit. That's like. And also, this is a free if you have any questions about the presentation, I won't be using online. You can also entire time for engineering. Ask to sign up to the QR code or the link. Get off the slides. A free version that should still be that as well. You just won't be able to access the link. So just again, this is just in the past generally has better decompilation resources. I have the so first of all, I have a link up here that you can visit. That's like. And they also I won't be using online. You can also time for engineering. Ask to sign up to the QR second bullet. Get off the slide. A free version that should still you just won't be able to access the link. So again, this is past general details better decompilation resources. I have the so first of all, I have a link down here that you can visit. That's like. Okay. So, yeah. So a working Linux environment would be good. So first of all, like some of the common tools, GDB, Ltrace, object dump. Most of those should be generally installed if you like just have like a plain Linux thing. The other thing is GDB itself is a nice debugger, but it's very hard to it's kind of a little bit hard to work on its own. So I recommend you install something called Jeff or PwnDebug. These are two different plugins that are built on top of GDB and will make the output look a lot nice. Make GDB a lot easier to use. If you don't have Linux, if you don't have been able to install Linux for some reason, just use your, you have, if you're a CS major, you have access to the UTD CS1, CS2 servers or CS grads if you're a grad student. And you can use those, you can use that SSH server, and most of these programs should be installed, though you have to install Jeff. And then there's a link for all the other reverse engineering files, which I'll be looking at. And so previous work, so last year I did a talk on reverse engineering. Here's the video link, and then slides if you want to copy that. But those are, I won't be, so because I've done it already, you have the material, you have like the video. I won't be going over the same thing. It's a waste of time. So I'm going to kind of do a little bit more going through like some demos instead. It'll be the same material, but in a different way. And then, so that is, let me actually, let me make sure the, okay. F11, oh, yeah, I think I do not, okay, so I think, yeah. Let me make sure that this one is still running. So question should be still running, but I'm not going to, that's my email. I'm not gonna do that, so let's go look at some stuff. So first of all, I will open up the, so this is what the slides I was talking about from last year. This is a slides that kind of goes over a lot of in-depth about some basic reverse engineering stuff, like kind of how binaries work. So I'm just going to, I mean, this is a good read and a video attached to it, so I'll leave that there. But today I'll be doing something different. So here, has anyone here programmed in C before? C or C++? I see someone shaking their head. Okay, but yeah, so C, what do you, so have you guys ever done it on like, do you always do it in like Windows or in the Windows environment, or like, have you ever done it in a Unix environment? Okay, Windows, Unix. Okay, yeah. Have you ever done like Unix and C and C++, you should have done this depending on the class. So when I want to compile a file, what command do I usually run? Or a C program? Oh, okay. GCC, yeah. So here I'm going to, first I'm going to show you what this program is. So if I open up in Vim, you can see this is a very simple program. It prints out 2 lines, hello world and then bye world. So this is just going to be our example program. So let's say I just want to compile it. If I compile it with GCC, it'll create, okay, let me do this. So it'll create, you can see, has some random stuff. So if I compile this, it'll create an a.l file, and then if I run it, it'll run whatever I just compiled. So I will compile it with a few other flags. So this one says create the file, go output it to ex1, and this one says this one you don't need to worry about. So if I decided to measure how big the file is, it tells me this file is 16 kbytes large. So that's a large file, basic for like 2 lines of C. So obviously there's a lot of stuff inside there. So what is in there? So you could, if you look into the file, you see there's like a lot of code and a lot of header information and a lot of padding. So it's a relatively decently sized file with a lot of complexity to it. So yeah, so let's say I don't want to compile it all the way. So GCC has a command that lets me compile it halfway. So let's say I just want to do this way, do a -c. Does anyone know what this does?
It's like a building a machine language, right? Like machine code, but not in binary.
Yeah, that is pretty much it. So basically what this does is it takes the C file, this ex1.c. So let me actually make a new directory, and then so that way it's not so crowded. And then let's copy ex1.c into here, and then I have to run this. Then I want to run C. So what it does, if I run this, it will actually create a file called ex1.o. And what that does is it takes the C file and then compiles it to machine code. But then it doesn't do something called linking. And this linking step is the step where you take all the, what you call the .o files and put it into one binary, into like a program. So these .o files are called object files. And then if I look at the file size, you can see compared to the previous one, this is at least 10 times smaller. And this is rightly so because it didn't compile any of the random other junk that a program has. So there's still quite a bit of stuff in that. And probably we won't go into what that kind of fluff is, but it's a lot of header stuff, a lot of other information that we don't really need, or like what we wouldn't see as evident immediately. But obviously the compiler would need it. So let's say I want to do something else. I want to just compile it into compile it, but don't assemble it. Don't create the machine code. So what I can do instead is do a -s flag, and this will create an assembly file called ex1.s. So unlike the other files that the compiler generated, this one is plain text. So you can see here the hello world string, bye world string, and then you can see here there's a couple of puts that are being called. So this one, if we look into this file, we can see that it calls puts, and then how does puts know what string to output? So we look right before, we have this instruction that loads, interestingly loads some value, this value into this value. And if we look at what this one is defined, it's defined right here. Essentially, what it's saying is load the address of this entity relative to the current instruction, RIP, and then load it into this register called RDI. This is x86. Yeah, so most computers that you run use x86. Yes?
Is this like MIPS?
This is, oh. Oh, yeah, I think I know. So this one, I think is because it automatically sets the formatting type to MIPS. So if I set to, let's say NAS. So that's just what that MIPS thing means. So I think I don't know if there's a, so I think, so basically what I've done is just kept it at MIPS because this is just, this thing is just like the highlighting in case if you're wondering. Has nothing to do with the actual language. Them is just dumb. But this is x86. And this is the assembly that most computers run. Specifically, this is the 64-bit version. And in 64-bit, we have these registers that are being passed as arguments. And that's what you call a calling convention. There is more details in the slides. It goes into more details about how this thing mechanic works, but yeah, we're just going to leave it at that. So some other instructions that are interesting is like you have pushes, or you have moves, which is like assignment, and then you have calls, which call functions, and then you have ret that returns from functions. These are kind of some of the instructions in the x86 assembly. So let's try to take a look. So this is our assembly, and we know this looks very similar to what our C code looks like. I mean, what the kind of the semantics is very similar. But let's try to see if that is the case when I try to disassemble this file. So if I try to open up this file, you can see it's just binary data. And you notice that there's some strings that are interesting, like the hello world, bye world, and then otherwise, let's see, what else? You have this puts string right here. So there's some strings in here that mean something, main, but most of this is like kind of gibberish because this is machine code. So let's say if I have machine code, I want to disassemble it. So if I run this command, you will see that it print out some disassembly. And just if you're wondering, this one I've actually I did an alias where I always change the syntax to Intel because object dump will default put it in AT&T syntax, which is horrid, and no one should be programming in AT&T syntax. And this is basically how it looks like, I think. Yeah, so this is what it would look like, and this is what looks like an Intel syntax. But this is just, so there's this command or argument that I usually do. Let's see. So if I try to, now going back to this assembly, I have this code. Looks very similar to what we have in the assembly. And for reference, I'm just going to go open that up as well. Except you have all these dots here that are not present here because these are like macros and like other random, like kind of more high level stuff, I guess descriptors, but they don't show up in the final code, at least not here. So we can see that we have looks very similar. The code is similar except for a few places. So notice how these 4 instructions, they're kind of weird. Why would I say weird? So this call 10, what is it doing?
Calling an address, like data from an address, in this case the hello world.
So yeah, it's calling at address 10, which is actually here, the next instruction. Similarly, this call 1C, next instruction. So there's something weird going on. And if we look at these instructions, if we look carefully, these are not actually correct either. LEA RIP +0 is just referencing this address, 0B address. Likewise, this one is only referencing this one. So why is that the case? Any ideas? So turns out when we're looking at a .o file, there is something called relocations that where there are certain places where you have to put placeholder values. Because remember, this .o file is actually machine code. But sometimes there's some addresses that we don't know how to access yet, or we don't know where, whether it's a string or like a program, or like a function to call. So here, for example, this call instruction, we don't know where to call puts. So obviously we know this one is a call puts, and same as this one, because that's what we saw in the original assembly. But then here, we see that the call is, we don't know where puts is. Puts is definitely not implemented here. Puts is implemented somewhere else. So what we can actually do is, if we do a -d and R, this will actually give me some more information. So might have to do that. So we look at this. You can see that this LEA, what comes after it is this relocation entry that tells me, hey, this 7 has to be located to this, relocated to the symbol called RO data -4. And then this one is, you have to relocate to RO data +9. So these are instructions, these are like some value somewhere else telling the linker, hey, these values need to be rewritten later on. Same with this one. Puts has to be, the call to puts, this has to be rewritten somewhere else when we finally know where puts is located. So these relocations tell us, tell the binary, this is how to find what symbols do we need and how to rewrite them. So first thing, now I want to go and open this in Ghidra. Open this file. Turns out Ghidra does not like it. So I will instead open it up in IDA. So if I try to run this, open up in IDA, okay. What we see here is we have two functions. A main function, which is what we created, and then this puts function. I don't remember defining it, but it's here. So what we have here is we have the same assembly that we had before. Here, IDA gives you a very good information that this S string is this string called hello world, and likewise this by world is this string right here. And you can see this kind of makes it very clear what it's actually doing, or where the strings are located. And in these calls that we mentioned, that I pointed to earlier, these are actually puts. If I double click on it, it's actually to this puts function in the what you call extern section, or external function. So what I really like about IDA or like Ghidra is they let you decompile this code as well. So watch. So if when I press F5 on here, oh, it just recreates the assembly code. It's a little small. I don't know if I can make it bigger. But yeah, this is literally the same code that we just wrote, and now IDA is able to reproduce that. And later when I open it up in Ghidra, it's the same thing. So that is the first kind of looking at that. Let's see. So there's a little curious thing. Wow. Let's try to go a little forward, and let's now try to compile it. So earlier I've already compiled this and linked it into this binary called ex1. And let's disassemble that as well. And then as you can see, this is a lot larger. And then a lot of these functions, a lot of these functions are basically default functions that you don't need to care about. So as kind of one side point when you're looking into reverse engineering, it's generally like you have a lot of code, and a lot of the code is useless, or it does stuff that you don't really need to look into. You just have to have high-level ideas of what it does, and then just move through it. And that's one of the ideas for reverse engineering. So here we have the main function. And we can see here, it now calls puts properly. And then this one, the LEA, is actually now points to a string. Same with this one. Well, it doesn't say, this one doesn't give me a correct name, but that's just object dump being dumb. So this puts has an interesting @plt after it, which is interesting because I call puts. I didn't call puts @plt when I called the function. So if you remember, there's actually the @plt here as well, even though clearly in my code it's just called puts. So we look and see where puts is, @plt is. We can see, we don't see a puts, but we see a puts plt right here. It's very short. 3 lines of assembly. Turns out that is not the implementation of puts. That is just a small function that's pointing to that's saying, hey, locate where puts is. And this is a little bit, if you want to look a little bit more deeper into that, this slide, we look at this slide, this one actually gives you a good diagram of how the entire process works. This is kind of the process, this process kind of shows you how any like binary is able to locate a function that is not located in itself. So puts, the real implementation of puts is actually located in what you would call the glibc, which is the standard C library. So this is just a bit of stub code that's saying, hey, just jump to wherever glibc loaded have puts. And this is very useful because now we don't have to have all of our code in one binary. We can have code that calls other libraries, and those libraries can just be loaded into lots of programs, and you have the same kind of base library code. So, okay, we have yeah?
So where's puts then?
You want me to go there? Well, we can do that. So, now introducing GDB. So debuggers are very cool because they let you to debug live binaries, and you can step through them. So going back to the slide, there is a slide that has all the commands for GDB, and you can use that to do like a reference guide. But what I will do is, if I run GDB ex1, you can see I am using GDB Jeff right here. So, okay, so let's do that. So I'm running with GDB Jeff. This, and hence it looks very colorful. If I just open it up in like GDB, so let me see, what was the command that says do not no init? Oh yeah, so nh. So this is if I were to just run it in a regular one. If I were to start, it's kind of difficult to work with. It doesn't give me a lot of information. This is like base GDB. But if I run it in Jeff, you have a lot of, it shows you a lot of stuff, a lot more stuff. And this helps, this is like kind of nicer. If there's like a similar one for pwn debug. Let's see. If I think I have this, which should be the pwn debug one. And then this is what, wait, that is weird. Okay, I think Pwn debug is broken, so we will ignore that. Okay, so what is cool about this is we have, it shows you the register values. Registers are basically like variables that you can access very fast in like a CPU. And then, as you noticed earlier, there are some like names of different values, and each of these are called registers, and you can like assign values, add to them, do arithmetic, and all that kind of stuff. And those are, some of them have special meaning. Some of them you can just use, but all of them you can actually use for general calculation. It's just that some of them have special meaning, and if you try to use them in different ways, it might crash the machine or the program that you're running, not the whole machine. So here is GDB. As you can see, it is stopped on the main function. It's not at the very top, but it's basically stopped right there. If I try to, now I want to step through it. So here I'm calling puts, and you can see here, it even GDB Jeff tells me that I'm calling puts, and the first parameter is this hello world string. And if I do that XS, it'll print out the string that says hello world, and so that's what I'm printing out. So if I step through it, you can see now it's jumping to the calling the PLT procedure. And you can see this jump is jumping to somewhere, some value, some memory value. If I actually, so it's doing this jump indirect. So what is this? Is there's a, at this memory address, there's a value. If I try to print it out, at that memory value, is this value right here. So what do you think would happen? What do you think will happen when I execute this jump instruction, this indirect jump? So you see this is an address. This address is a pointer to some other address. And that's probably what we're jumping to. Do we see this address anywhere?
It's the next instruction.
Yeah. So you notice that this address is actually just this address. And if I step once, indeed I just jump to the next instruction. And then I do some more instructions. It jumps to here. And then it initializes other values, and then it jumps here to this DL runtime resolve X save C. And this basically usually means that you are accessing some internal libc function. So I'm just going to go fast forward it, and then it does a lot of stuff, mainly saving registers, searching for the function, and then doing more stuff. And then finally, we are here at the last instruction, and when we jump to puts. And then that's kind of how the entire linking works, or almost entire. So if I run through puts, I'm going to exit out. We see I am now in the next instruction. And in this one, I'm calling puts again. And this time I'm calling it with the parameter by world. If I do RDI, you can see that this string is help by world. This address is, this argument is the string by world. And then if I run, I go back to the PLT function, or puts PLT thing. If I jump, but this time, let me first dump this. So if I dump this is a completely different address. So let's watch as I jump again. It just jumps to puts. So this is really cool because essentially what it's doing is the first time it resolves where the function goes, and then every subsequent time you just jump directly. You don't need to go through the entire resolving process. And then we go here. We see that it prints out this by world. Yeah. And then that is a general. Oh yeah, and another thing with the GDB that I didn't show. So I run this instruction called SI, or command, which means step through one instruction. And sometimes I run the instruction NI. Let's see, where was it? Well, it's up there. NI basically says, call this function. If it steps through one instruction. If it's a call to a function, it will basically run until you exit out of that function. So it's useful if I don't want to go into a function. And then fin means to run until I exit this function or return from the function. So that is a general run through. Let's see, what else? Yeah. Let's see, what else other interesting commands? Oh yeah, R run, C continue. So R means to start the binary all over, run the binary, and then C means continue running until it reaches a breakpoint. And what's a breakpoint? This instruction lets you to set an address that you want to break the program at. So let's say I want to stop the program. Let's say after this loop, I just find the address to that loop and then just set a breakpoint there. And of course, if you ever work with a debugger, like not GDB, like a high-level debugger, you can actually set it. You remember you can set a breakpoint on like each line. That's kind of special because you can do that because when you compile as debug mode, it'll save the line numbers in the address mapping. So each line number corresponds to an address in the low-level instructions, and then it'll just like automatically remember that, and it'll just whenever you say break on line 7, it'll just search for what address is corresponding to line 7 and just break there. And that's kind of tricks there. If I wanted to do that, actually, I would need to compile this. What was it? This one. And then I need to put a parameter called -g to compile it. And then when I do this, what was the here, if I want to do a breakpoint on EX1 line 4, actually, no, it's kind of boring. Let's do line 5. And I run, it'll stop right there on line 5, which happens to be this instruction, which you can actually even see the source code if you compile a debug. So you can see I'm right here on this line corresponding to this address. So that's kind of a cool little thing. And then what else? And then next, yeah. So these are N and I, step and next. Step I can be abbreviated as SI. Same with next I with NI. So set values. X allows you to examine or print out the memory of a particular value of a particular address. So you saw me do that when I was printing out memory for like certain pointers and stuff like that. P means to print out a variable. So if I go back here, if I want to print out the value of RDI, I can just do that, and it will print P and then RDI. And that's kind of idea. Then disassemble. If I do this as, it'll disassemble the function. It'll even tell me where I'm at. let's see. I don't see any other questions, so I'm gonna keep going. So now, it looks like we now want to go to final demo. So how does this look like for like an entire reverse engineering thing? What the heck? Okay, so let's do, so here, this is actually, so this program is actually, when I go into CTF UTD CSG, this one is this thing. Okay, I hope I'm not. I didn't. So this is this problem right here, which I can download. Oh, someone already solved it. I hope more people will solve it after I go over this one. So this is the download. So this is what I'm going to look at. So when I unzip it, it gives me 3 files. This one is some basic instruction. There's some videos you can watch also. But I'm just going to look at this binary. So first of all, if I try to dump this is like a very large binary, or like relatively larger binary, so probably let's not use object dump unless you really want to look at assembly. So what I will do is open it up in Ghidra this time. Actually, I don't think Ghidra supports command line. So what I would do is import this file. Okay, let's see. Gosh darn it, I think Ghidra is broken. Yeah, I think Ghidra is definitely broken. Yeah, I have no idea. Okay, I think Ghidra is broken, so I'm going to not use Ghidra. Good riddance. Okay, so this one is a small, like, this is a program. Oh yeah, one other thing. I wanted to do this first. Let's see if Ghidra opens up this file, or is it always broken? Okay, so let's do this. Let's import this file. Okay. What version is this? This is broken. Okay. Yeah, I think I won't toy around with it. So let's open up this EX1. So we open up EX1 again. We can see that once again, the main file there's a lot of functions here, but then the main is the only one that we actually defined. And you can see that this will call puts, and then stuff like that. And then F5 is your friend, because that is your to decompile. So this one, let's look at this reverse engineering challenge. So we see here that this is actually, we look at this control flow, we can see that this one has, each of these is like a branch. So it's kind of like an if-else kind of thing. You can see that if it goes one way, it goes here, otherwise it goes in the other direction. And you can see that we probably want to get to this branch because it seems like these fail really quickly. and we look very carefully, this one prints out error, this one prints out an error, this one prints out an error, and this one is actually where we want to go to. So we want to somehow pass all these checks, or somehow do that. So let's, we can, so there are two ways. I mean, you can look at here, I will go look at these, yeah, I think the assembly looks a little intimidating. So let us do decompile for the moment. So if I try to, wait, what the heck? Okay, did I screw something? Okay, there you go. So here, if we look at kind of cross-reference, you can see the first one is some sort of compare with 1, CMP, and then this is a jump if 0. And you can see here, this corresponds to if arg1 equals 1. And then we can see here, there's something that says usage, and then some x, and then just exits out. So this is probably where we probably don't want to go here. So we probably want argc to be equal to something else. So essentially we want to pass an argument. Okay. So let's look at this. We can see the next thing prints out something, and then some more stuff. It does this stir comp here. And what it's saying is, compare this with this string right here. If this is true, i.e. this is equal to 0, meaning if it's equal, then it goes into this thing. It says, you found the fake flag. So this is probably not what we want. So we wanted to go to this code right here. So we look back here, we can see that this corresponds to this thing right here. The string that says welcome, and then some other strings, and then you can see this string this says this is a fake flag or false flag. And then you can see this interesting instruction, rep e cmp sb. So this is actually one of the intricacies of x86, where you basically have every single instruction that does everything in x86. So this one in particular takes the registers and then compares two strings to see if they're equal. And if they are, you just keep comparing until something happens. So this is some low-level primitives to basically check if the strings are equal or not. I would recommend, if you want to look more into it, look into the Intel manual for this. It's a little complex. So here is this code right here. And what we see here is a bunch of XORs happening. And we can see here there's some sort of XORs happening. And then there's some referencing some memory. And finally, this function right here, which, again, because of how this is compiled, some of the symbols do not get resolved, which is a little bit frustrating. So this one, if I remember correctly, if I can, this is annoying because I need to actually dump it. So we can see here, this 1080 is actually stir comp. And this is the same thing right here. So this is just stir comp. So here, this is the first time when sometimes IDA does not give you good output. So you have to modify it, modify the decompiled output to make it look nicer. So this is an example. This is a stir comp. So here, I basically said, yeah, just do that. I basically just press N, and this will rename this variable, or this function. So this obviously still does not look right. because this one should take two arguments, two string arguments. So what I want to do is change the type. So this y will do what I want. I want to say it passes in two arguments, two string arguments. So if I do that, I get this. And you can see that the first argument it's passing is this y7. And this other one is this v3, which if we look up here is actually just our argv. So which is the flag that we are giving it. So here, we're saying that if string comp returns 1 or non-zero, then it says this is not the flag. Otherwise, it says you found the flag. And that's the flag. So now we are actually very close to finding the actual value. So now we have this final part, which is doing some XOR operation. So if I look at data, we can see that each of these are actually corresponding to some part of this string. And this data is actually just every byte is being XORed AB. You can see what it's doing, right? So let's do this. So this obviously looks is also not really pleasing data. So I want to change it a bit. Actually, what I can do is, let's see. Let me make it bytes instead. So when I had IDA, I actually had like a plugin that lets me do this. And then there is a value where I can actually do convert to a Python or C++ or hex string, so like bytes. So I can copy that out. Let me double check what it was again. I don't remember what it was. If I remember, it was this. I think it was this one. Yeah. So it's this one. If we want to, lazy IDA, I believe was the name of the plugin. And if we look at this, is this thing right here. And it has these functions right here. So that's what I'm doing. Obviously, if you don't have that, you can just copy this and then like manually copy the hex out. But I'm just going to do the shortcut way and copy that. So why am I copying out the hex? I know that each of these bytes is being XORed AB, AB. So I want to be able to, if I want to decrypt the string, I just XOR AB everywhere. So if I open up, now there's an online tool that is very useful called CyberChef. And what it does is you can actually give an input, then do like various encryptions. Oh, and I forgot. I need to also from hex. And obviously, I don't think I copied everything. Yeah, no, I don't think I copied everything. Huh? Oh, the last one I did not copy, D6. Yeah, so that's the flag. So that is one way of solving it. Like, so this is the idea of, I'm just going to go look at the code and do static reverse engineering, which is a fine way to do reverse engineering. Sometimes that does not work. So what I can do instead is I can do some dynamic analysis. And sometimes you'll find this way easier. So I can run it in GDB. And then do a run. To pass an argument, I can just do this. Run and then pass the argument. And then it will run it. So I wanted to just start, pass the argument, and then just step through. So here, let me actually restart it again. So here, I have this call function. I don't want to go step into it, so I just do NI, next instruction, so I can skip over it. And that's just something so that you don't make your life too difficult. So let's see where I am. I'm at the start comp right here. And you can see that it is actually calling the start comp and then just comparing it with my input. And then here you can see the flag once again, right in plain sight. And you don't even have to go through all that hard work of reverse engineering. But wait, there's even more trickery stuff. So there is a tool called Strace that lets you basically trace any program and tells you all the system calls that it's making to the underlying operating system. So when I run it, I can see that it's doing a lot of system calls. More importantly, I need to pass in an argument. And you can see that it is printing out, every time it prints out some strings, it actually says that it did something. It did like a system call to write to the console. So you can see that every time it writes, it says sorry. It basically says that it wrote it. And then if I read some input, well, it didn't read anything, so you won't have that syscall. So this is useful for certain programs that do a lot of syscalls. This is not so much. This not so much. So there's another function, another program called Ltrace. What it does is it traces all the library function calls that it makes. And it completely failed. So turns out Ltrace is not really that great. Sometimes it fails. But let me do. So looks like that doesn't quite work. But anyways, theoretically, I can. I think I know why. But if I do Ltrace, let's say on a program that I know it works, it tells you all the library calls that it calls. So here, I know that if I look at the first example, it calls two functions, and it calls puts. So, yeah. Sometimes Ltrace does not work in this. It looks like in this case it just doesn't like the how it's compiled. So, yeah. What else? Let me see if there are any questions. Okay. So, I believe that will be about it. Obviously, didn't really like how this just failed. So, let me actually do this. So, he also released the source code. And then this is how you decrypt it. Let me decrypt it. And then, let's see. This one has the code. Let me compile that in a way I know that works. Okay, so let's do this. So I do this, Ltrace, and yeah, now it works. So you can see here, this stir comp is actually being called, and we obviously see the flag right here in plain sight. But sometimes it doesn't work, as clearly you've seen. But yeah, these are kind of, so that's kind of how some ideas for reverse engineering. There are in the challenges, there are 4 more other challenges that we put out that kind of are a little bit more difficult. But if you want to practice reverse engineering x86 Linux stuff, that's where you can start. And we also have a lot of problems in other categories as well. Web, crypto, Pwn, and some other stuff. So definitely feel free to play around this if you have the time, want to practice. Yeah, that is about it. Are there any other questions? Okay, if there are no questions, I will end this presentation.